Well, the idea that maybe gas tubes instead of vacuum tubes, but still electronic devices, would be fast enough and cheap enough for me was helped up quite a bit by the fact that RCA during the 30s, when I was working on these things that are sinus, brought out a trigger tube, as they called it, which did not use any heat as vacuum tubes normally do to get electrons. These, like the neon tubes, worked with gas, and they were fired, that is, started off by putting a voltage on one of the wires, one of the electrodes here, and that would start a current in the gas, which current would continue. They called this kind of a relay tube. It was to use a very small signal to actuate something else which required more current, and thereby would turn on even bigger things. And in their own design, the intended use for this was that the original trigger would be actuated by a very weak radio signal. And so by connecting this to a relay, then every time the radio signal occurred, why, this would turn on the relay, and the relay would turn on maybe an electric motor, a garage door opener, what have you. And perhaps they were going to put it into TV sets to make remote actuation of those possible. There were a lot of things that could be looking toward the future, but in the 1930s, this OA4G tube was listed in all the catalogs and available in the radio stores, and so I bought quite a few of them to see what I could do with them. So I tried then to make a circuit which would be part of a computer, which would store numbers and advance on counts in the same way that the ultimate counter did in the ENIAC, except this was the cheapie. This was the one which I could construct at Ursinus College without any Army Ordnance budget, just out of my pocket money, and try it out. So this board, which now has 6 sockets on it, has to have the 6th socket there purely for any extra use. It was a spare. What I was intending here was that there would be just 5 tubes here, and they would interact with each other much as did that little neon thing that I first built, which was binary. In this case, when one tube went on, it would turn off the others, and so on, but connected around in a ring, so that with a ring of 5 of these, I could then count up to 5. And combining that with a binary counter, which I knew I could do cheaply then, if I could make this work and that, 2 times 5 is 10, and I would have a decimal system, a counting system, for not peanuts, you might say, but for something the order of $1 for each of these tubes, you might say. Maybe for $10 I'd have the whole thing. And I wouldn't have to supply a lot of electric power. I wouldn't need a lot of storage batteries or other sources of direct current power. And I wouldn't. The other disadvantage of power, of course, is that with it you usually get a lot that you waste in heat. And so for all of the use you make of it as far as handling information is concerned, why, you sometimes get 100 or 1,000 times as much electricity, which turns into heat that's just a big disadvantage to you. So here was something which didn't require that much power and therefore it didn't produce that very much heat either. Just the small amount of current then that could be triggered, and only one tube would be carrying that current out of the 5 at any one time, and it would be just a question of this indicating which of 5 pulses had come. Was it the first pulse? Then the first one turn on, the second, and so on. You go around, and when the 6th pulse, well, you're back to the beginning here. And there are various ways of making this into a counter of count 10s. You can either have the binary counter follow this or precede it, so that this only gets every other pulse of what you're really interested in, or that you can tell how many times this has been around by looking at a binary count. After this thing has been around once, why it'll trigger the flip-flop to say, all right, that's once around, now another time around, and so on. And of course from that you also derive carry pulses, so that you could go into a similar thing. And I already had wired up. Here's a board that's almost completely wired, but without the tubes at the moment. And that is identical in construction to this one, insofar as the mechanical features and the condensers and everything that I had there. You see, each of these has got the things that I was then using at Ursinus to experiment with this ring around scale of 5 counter. For some of the more simple-minded work, why here, for instance, is another version of just putting 2 bulbs and some resistors and things together here to do what was done on that first counter we saw. So there are lots of these things which were, here's one with condensers and other parts to it, all of these things which are leftovers, you might say, from my work at Ursinus. And now there's one little thing we come back to again, that is that these things work better if they get standard pulses. So just making and breaking a contact, as I did in the demonstration on the simple one to begin with, is not the preferred way if you want reliability. So to test these out, I had to have several other pieces of apparatus. I bought oscilloscopes where you could see what was happening. Well, those are very common instruments nowadays. In fact, practically anybody entering data into a computer has a glass tube in front of him which works like a TV tube, but is showing him the data as it appears on a screen right in front of his eyes. In those days, an oscilloscope was a brand new thing in the physics laboratories for teaching. So that I bought out of the school's money. I bought an oscilloscope. One of the first schools, I think, to use an oscilloscope in the 30s to help teach and show people in these classes what sound waves looked like, what electrical things looked like, and so on. And I don't now have that because that oscilloscope belonged to the physics department, and I left it there. And they probably had 10 more each, an improvement on that as time went on. So the first scope I bought from a place which was manufacturing an all battery-operated oscilloscope, they shipped it to me with the batteries in place, and everything broke up everything as the batteries broke loose of their moorings inside the case, and I had a month's work just getting that thing back together again. But Coltman and Romander, the outfit in Brooklyn, I guess it was, or Newark, were very sorry about it all, and I forgot whether they took anything off the price. But that little 3-inch oscilloscope was my first teaching tool, connecting visual indications with the kinds of phenomenon which we would want to use in physics demonstration. So outside of the physics demonstrations, well, I could use that to look at what was happening here. These, of course, had the advantage that you actually could see a visible glow for the tube that was on. So they were like the neon tubes, had an indicator function as well as the counting and storage function. But still, we had to know what kind of pulses were going in and what was happening in the circuit. And for that, I had to build a pulse former. And so somewhere, oh yes, right here is a rudimentary form of pulse former. And what do we have it made out of? Well, of course, here is a device which I'd scrounged somewhere, which is a choke, an inductance. Here is another kind of gas tube, which was used in the sweep circuits of oscilloscopes in those days, an 885 or something like that. 884, that one is. And then here's a power tube, a 6, what is it now? But you notice it has a screen grid on top there. It has a terminal on top which goes to a screen grid, or a control grid maybe. And it's a 6J7G, I think. Well, you can begin to guess the era in which these things were manufactured, because not only do you know the tube type, but you notice that letter G. By that time, they'd learned how to make metal tubes, and many tubes were made in metal. Less breakable, but had other disadvantages. And so you could get the glass type with the G, or you could get them without the G. This combination of tubes then produced the pulses with which I tested the counters. And that, plus the test instrument of an oscilloscope, enabled me to know more or less what I was doing, find out what frequency I was counting, when the thing was reliable and when it wasn't. And these switches were merely for controlling things like how wide was the pulse, how high was the pulse, and at a repetition rate, how frequently did the pulses occur. So I could determine that I could count with these gas tube counters at least 500 times a second. It began to be a little doubtful as to whether they would work reliably at higher rates. And that really didn't concern me too much then. The thing was, did I have it in my power to buy things of this sort out of my pocketbook, put them together, make them work, and work reliably enough that I could use them for my purposes and save myself a lot of work and get things done much faster. I was, as I say, interested in making statistical analyses of geophysical and weather data in such a way as to prove, if possible, the possibility that the sun, for instance, affected the weather. Years later, I got a little closer to the Earth. I proved that the moon affected the Earth's weather too. But these things are still in a form of incomplete understanding. Nobody knows why the moon or how the moon affects our rainfall, which it does, and nobody knows why or how the sun affects our weather. But we're beginning to get other people interested in that now. This was in the 1930s. Now in the 1970s, 40 years later, they are beginning to look at some of those exterior forces which could possibly affect the weather, and beginning to believe that they really do, and maybe it is worthwhile to find out. Just on the radio today, I heard an expressed concern over the fact that some of the wide variations in weather now are wider than have occurred in the last 100 years, and people are beginning to worry as to whether there will be worse dry spells and crop failures and things of that sort than we've had for a long time. It's important to know. But it takes something, of course, to make everybody worried. It took the World War II to create this particular emergency in which the electronic computer got its tryout. Before that, people weren't willing to make the effort to try it. The effort including, of course, allocating money to it as well as time. Somebody has to make that effort before you'll ever find out. It's unfortunate that a war sometimes has to be the fundamental cause of making an effort into something which is so rewarding as computers have been, their scientific uses and so on. I think it's unfortunate that we have to have famines or other losses of food sources and things before we really get interested enough in the weather to follow the leads, which I've thought were worth following for 40 years. But in the meantime, let me go back to the problem of computers. I had one more way in which I sought to get a cheap source of a computation to help me in the reduction of data, and this was an example of an analog computer which I was able to use very effectively in analyzing things like the rotation period of the sun's influence on the weather and so on. The harmonic analyzer, which I built, was an analog device because the accuracy required of it was not very great, and the abilities to build this and even to design it were within my powers. I could easily see how to do this, and I thought it would be useful to me. And so there is such a device, again, built out of the same kinds of materials, you might say. This stuff is wall board, pressed board. I think it was made out of sugar cane originally, but I bought it as building supplies, of course. And that was easier for me to work with than panels of wood. And I mounted my sockets and did all the things I had to do with all kinds of surplus things that I'd bought in these markets where they took apart and bought up old radios and got parts which the radio manufacturer decided he didn't need to use anymore because he discontinued that model and so on. Profited by the switches, the condensers, the sockets, everything practically was on the cheap side. But it worked. And if I could now get that harmonic analyzer. What we see here is my version of a cheap instrument to do the analysis of data into waves, and in particular sine waves and cosine waves, which are the standard kinds of waves into which mathematicians and physicists and others usually analyze their wave motion. And this has to have a lot of knobs for the entry of the data. Nowadays that would seem rather foolish. Why, you just punch a keyboard and put it into a computer. Or a little earlier than this, you punched a card, a punch card, and that somehow conveyed it to a computing device. Or in some cases, you punched holes in a paper tape, and that went to a computer. But here, just as in an adding machine or a desk calculator, all the data is entered at the keyboard or the operating position of the computer. Here, all the data is entered through turning and setting knobs, and the readout is the numbers that I'm interested in come out on a meter here. So here's a different kind of thing that you do when you're trying to make an analog device serve your purpose. You want these knobs to act in a reliable and accurate fashion, but you're not insisting on perfection. You don't get it either. You want this meter here to be as reliable and accurate as you think the rest of the device is, so that you don't lose any accuracy purely because the meter is sticky or wrong. So if the meter has a bad pivot or bearing, why, you may not read right. There are other things wrong with it. But what you do is spend your money then where it counts the most and does the most for you. So this was a good meter in its day and for its class. This measured microamperes because the currents that it had to measure were small, and the computing here was done by a series of circuits inside and underneath this board, which were responded to voltages which could be changed by the setting of these switches, these dials. You can see the handwork involved, incidentally, in that each one of these dials, there's a paper front to this thing which I pasted on. It's a little dusty and dirty now, but after all, this was made in the 30s. This is about 40 years old. And so during those 40 years, I have not used a duster or a vacuum sweeper on it, as far as I know. Just tried to sort of blow it off. And I've had it operating several times in the past 10 or 15 years. I know it still works, but it's cumbersome to use compared to present-day devices, of course. So the next place you put your money is in buying the part that's underneath the knob here. That was a General Radio potentiometer, which was guaranteed to be something like 1% accurate or so. So that if you could set the knob to within 1% of its full range, well, you might get a voltage taken off from it, which would be within about 1%. But then, of course, that voltage, in turn, through a lot of things, affects this meter over here at the final reading. And you've got two or three things more that affect the accuracy. For one thing, if all the readings were so low here that you couldn't see whether it was 0 or just off 0, that would be bad. You want to get full-scale readings if possible. So that's what the plug board's for. These are banana plugs used in radio and measuring circuits and so forth, which you can change and plug into various places so that the readings you want have a magnitude on the dial which gives you a chance at a reading within maybe 1 or 2%. So if the readings turn out to be small all the time, you change the plug board so as to get larger readings. And then you know what factor you should change those readings by, because you know where you plugged this. And there are marks along here which tell you by what factor you should account for the size of the reading. That's one thing that you have to do to get accuracy. All of the resistors in here have to be as accurate as the others. And so I personally measured all of those with a Wheatstone bridge and tailored them in some cases to make the exact value. I used pieces of wire which I could change and attach to different places, change the length of, and so on. Yardley or somebody made a stuff that you bought by the yard and cut it off to be approximately the resistance you want, and then I would tailor it till it was exactly that. But there's one more factor. Where did all these voltages come from? Where did the whole system get set up? It had to have a power supply. Now, unlike our digital equipment, where we may be content with voltages which are variable within 10% or so, and that was one of the things we did in the ENIAC, you remember, was to make the counting circuits so reliable that they would perform the same way and count the same digits and so forth, regardless of large variations like factors of 2 to 1 in voltage and other things. This, the very accuracy of the whole thing, depends on how good the input voltage, the supply voltage, is. Well, I was working in a physics building where the students walked up and down stairs, but there was a freight elevator. If that suddenly started operating, that would change the voltage. It took a big load. And there were probably other things. There were ventilating fans, particularly for the chemistry laboratory in the same science building with me, which they might switch on and off as they put something under the ventilating hood. There were all kinds of power changes which could occur. And this was not working from batteries. It could have, but I thought it would be better if I made something which would be what we call a regulated power supply. And here's my version. I can't quite see into it myself right now, but the general idea is that I first had a rectifier power supply from the regular house current, for which these various things under here were the parts. And then I ran the current that I was going to use through a lot of pilot lamp bulbs, which are incandescent bulbs, and they change their resistance with their temperature. And this, in fact, was used in such a way then to make them help to keep the current constant and thereby keep the voltage constant. And then up here are various other kinds of tubes. Another one with a resistance inside of it, an amperite tube they call it, which people were using for regulating voltages in radios and things of that sort those days. And then a lot of, again, neon tubes and argon tubes, gas tubes, which have the characteristic that after the voltage gets a certain height, they go on, and if voltage increases in the whole circuit, they still have the same voltage across them. So with using these various characteristics of things that were then available, and not too much availability before the 1930s, here were these gas tubes available in large sizes as well as the small neons. And with them and other things here, I produced something which allowed the outside house current in the science building or wherever to vary by perhaps 10 or 15%, whereas this thing would get something within 0.5% of what I was asking for. And with that kind of a thing built in, why then the analog computer could be relied upon, all in all, to give me an answer of about 1%. What you might say, it was a slight struggle. You had to think about what you were doing. You had to be sensible about it. But it didn't drain my pocketbook to the point where I couldn't do it. This then enabled some students at Ursinus to quickly run through a lot of observations which I had them work on, compiled from the weather maps, so they could not only say how much it rained over the United States each day, but with this, they could analyze that and say, to what extent were the rainfall variations from day to day showing a 27-day wave or a half of that, a 13-and-a-half-day wave, and so on. The results showed that the 13-and-a-half-day wave was apparently the one that stood out as significant. Now, in the statistical work of handling that, I had to have the results that came out of this, and lots of them. You can't do statistics on one sample. Everybody should know that. You can't do very good ones usually on 2 or 3 or 4 samples, and sometimes you have to have hundreds of samples before you can show that something is a little different from what it would be if it were just by chance. So that's what I was reporting to the Physical Society in 1939 at Christmas time, or 1940 at Christmas time rather, when I felt that the meteorologists weren't yet ready to consider things like that, and I took it to the physics chapter, or the physics section of the AAAS. I don't think that it made a big impression on the physics people either, but what I was doing in the general analysis of this data at that time was practically the same as what was being done by Bartels and Chapman and others in analyzing how the sun affected the Earth's magnetic field. And I felt that there was a clue as to how one might go about showing how the sun could possibly affect the weather. I'm disappointed that it's taken so long for people to get more interested in that. It has really taken the space age to accomplish this. The fact that we can send up satellites and probes and things of that sort way beyond what we usually consider the limits of the Earth's atmosphere. We get measurements from those things which we now see show variations of wind, as they call it, protons and electrons and things coming from the sun, going through the solar system, and those variations are actually very large, significant variations. Now that we can measure them directly, we have a little more chance of trying to correlate them with what we've seen on the surface of the Earth and what we call weather. We knew for a long time, the radio amateurs first found it out, that radio propagation conditions vary with the solar cycle, that is, with the 11 or so years of ups and downs of how many spots there are in the sun. We know more about that now, of course, than we did then. And most recently, for instance, we found out that there was a period in recent years, a couple of centuries ago, when the sun did not go through its usual cycle and had 40 years or so with almost no spots. And that is considered a pretty exciting discovery in itself. I've been much concerned with other features of solar activity which have been very lightly regarded and passed over. For instance, the fact that it was known by observers at the Greenwich Observatory in 1910 or thereabouts. They noticed that the daily photographs of the sun, which they were measuring, showed more spots on the east of the sun than on the west side of the sun. Well, east and west is a relative term. It means how we see the sun in a telescope. And so, by convention, why the side that's turning toward us in the daily rotation of the sun is called the east side, and the other side turning away from us is called the west side. So we see more spots coming toward us from the dark, or rather the invisible side of the sun. It isn't dark at all over there, of course. And we see more spots coming around the bend, as it were, on the edge, which we call the eastern edge. And then, as they cross, we see them passing as the sun turns and going across the central meridian and on toward the west and disappearing into the side we can't see again. They seem to wane. That is, there's less spot area, less spot count or number, all that. Well, for years, since 1900, there's 70 years or so which this has been known, and nobody has really investigated that or tried to connect it with anything. It's just sort of considered it's a peculiarity of the observations. There was a time during the 1930s, I believe. No, it'd be not during the 1940s, rather, when just about the time that we were going to install a UNIVAC system at the Franklin Institute, that the Institute, which has astronomical lectures based on our planetarium, decided to hold a meeting for a whole day as to what could be done with the computers in astronomy. And at that time I presented this problem of the east and west disparity and what could be done, for instance, putting all the data of the sun on the magnetic tapes which we made for the UNIVAC. I don't know whether they've ever put that data on tapes yet, but I think much of it now exists in punch cards and could be put on tapes. But the fact remains that while I've been busy working on all kinds of computer problems, I've not yet had the time to return and answer the questions which I believe should be answered with respect to this asymmetry, this apparent asymmetry, if you like. The sun really doesn't know east from west. All it knows is which way it's turning. And so if you put yourself in the position of an observer on Venus, the observer on Venus likewise would see more spots on the east of the sun than on the west. And if you were on Jupiter and observing the sun and could observe well enough to see these spotty reactions on the sun, well, again, you'd see more on what you thought was the east versus the west. And this would be true of lots of places where you could station yourself, that you would see some peculiarities or asymmetry. Why? And what difference does it make to us? Well, I know that it makes some difference to our weather, because strangely enough, the people in Spain who have tried to observe the sun say there are more spots on the west side. Whereas Greenwich astronomers, being very careful and meticulous in their techniques and measurements, average more spots on the east side. The difference is a rather simple, and I would think an obvious one. The people in Greenwich have taken pains to get a photograph of the sun every day of the year. If it's cloudy at Greenwich, they get one from Tokyo or Washington, D.C., or from Africa, or wherever the sky has been clear, and they think that's the best photograph they can obtain. The Jesuits in their station in Spain have no such facilities. When they cannot take a decent photograph, they just give up. They say that photograph's not worth looking at. And so they average only the days which they get good photographs of the sun, where the sky is clear and not hazy, and not cloudy, of course. It's fairly sunny in Spain, but it can be hazy. And so they have a selected group of solar photographs, and out of that selected group, they see more spots on the west than on the east. Well, that very fact, to me, makes prima facie evidence that whatever's happening on the sun with regard to the east and west asymmetry has an effect on the weather on this Earth. The Jesuits didn't know this was happening. They didn't plan it that way. They didn't arrange it or anything. It just happened that that's the way they did their observations. And the thoroughness of the British in getting solar plates every day from anywhere made the big difference in what they found out about where the spots are on the sun. Well, that's just a slight review, you might say, of a subject which I think will be awfully important someday. Let's break. Must be lunchtime.
Well, let's see. I guess, should I imply that I'm talking to you, or shall I?
Well, you can look at the camera.
Talk to the camera if you
Yeah,
like.
okay.
You can talk to me if you want.
Yeah, that'd be
Anyway,
nice
the
too.
general idea is that you, apparently along with a few other girls at Chestnut Hill, thought math was a very interesting subject, and you majored in math, and that's how you got
All right.
picked
All right,
up
well,
by.
Let her tell her
Shall-
story now, John.
Yes. Well, I was born in Ireland during the time of the Irish Rebellion, toward the end of it, as a matter of fact. And but my parents were of the persuasion that we should be exposed only to things that were Irish. So no one was ever allowed to speak any English to us at all. And so until the time when I was almost 4, when I came to this country, I had never heard English spoken at all, and neither had my brothers. So we moved here. My father had been imprisoned over there, and he escaped and came to this country and built a house for us and went into a building business with his brother. And when the house was all ready, he sent for my mother and my sister and my 2 brothers. We came out here, and I grew up in Chestnut Hill, and from there I went to Hallahan High School in Philadelphia. And when it was time to go to college, I didn't really know very much about college or what I'd want to take or anything, but since I was offered a very nice scholarship to Chestnut Hill College, which was right in the neighborhood, I went. And when it came time to make a decision of what I would like to major in, I chose my favorite subject, which happened to be math. I don't know why it would be my favorite subject. It was one of those subjects in which I did very well, let me put it that way, not that I knew a lot about it. So while I was still in college, the war broke out. And we were the first class to graduate with the war on in 1942. About a week after graduation, one day in the paper, I saw an ad where the U.S. government was looking for math majors. So in my math class at Chestnut Hill College, in my graduating class at Chestnut Hill College, out of the 78 girls that graduated that day, only 3 were math majors. So we stayed pretty close to one another and were very good friends. So I called one of them and said, how about going down and looking into this opportunity to be a mathematician for the government? So she and I went down to a place on North Broad Street, and when they only wanted to know whether or not we were math majors. That was all. And as soon as they heard that we'd had our degree in math, they, I guess, employed us on the spot and told us to report to the Moore School of Electrical Engineering the first week in July. So Fran Beales, the other girl whose picture you often see with the ENIAC, was the girl that I had gone to college with, the other math major. So she and I started, and as far as we knew, we were the first ones employed here in Philadelphia to work on this project. So when we showed up at the Moore School, there already was a nucleus of people from Aberdeen working there. They had taken over the Aberdeen Proving Grounds had taken over the differential analyzer at the Moore School as per some previous agreement. And they had a nucleus of about 10 people who were working there. And I remember the first day we came in, we were introduced to the people, and they were all very, very nice and very friendly, and said that our job was going to be to compute firing tables. And did we know how to compute a ballistic trajectory? Well, not only did we not know how to compute it, we had never even heard the words before. So they handed us a copy of Scarborough and said, well, this is the differential equations of this problem. Now, maybe read Scarborough and you'll find out how to do it. Well, we spent a couple weeks reading Scarborough and learned a lot of theory, but we didn't know how you went about computing a firing table from that. So then they showed us these great big sheets that they used, and we got to work. It was, once we understood what numerical integration was all about, then we got to work and started to compute. Well, we had only been there about, altogether about 3 weeks, when one day they came and said that they would have liked, who were the people in charge, that is John Holberton, I think at that time, said that they would like us to go downstairs to the differential analyzer and learn how to operate the differential analyzer. So Fran and I went down there, and we were trained on how to operate the differential analyzer, and we stayed with the differential analyzer the whole war. And after we got pretty well trained, then we were separated, and I was when I was on the night shift for 2 weeks, Fran would be on the day shift. That was the way we worked. They wanted to keep that machine working as many hours as possible, so they divided us into shifts. Well, it was turned out that the analyzer room was the only room in all of Moore School that was air conditioned. And we had started working in July of '42, and I guess it was a long, hot summer, as they describe it. And gradually we got to know everybody associated with the Moore School, because as the afternoons got hot, everybody from Moore School would come down to cool off for a little while. So the students would come down. There were a group who were working on the roof, Press Eggert among them. They would be out on the roof doing their radar, and they'd get all hot, and they'd come down. They're wearing nothing but shorts to cool off for a while. And then the professors would come down, and there were a number of Navy students there learning radar techniques, and they would come down, and it was just like a home for everybody at Moore School to come down to this place to cool off. So gradually learned the names of all the people. John was already there at the time, and Professor Brainerd would come, and Professor Wygant was I guess he was the person from the Moore School who was directly in charge of the differential analyzer. And so we had some great times during those years just operating that differential analyzer. And we did a lot of hand computing too, because every trajectory that was going to be run on the differential analyzer had to have a test run worked out by hand first, and then we could check that against the results of the differential analyzer. So we would hand compute, which usually took about a week to hand compute, just one angle and one muzzle velocity of a particular gun, and we would compute the trajectory and then check the results of the differential analyzer against what we had hand computed. So.
Now, do you remember the first time you saw John Mauchly?
I can't remember exactly the first time I saw John Mauchly. All the professors would come down, and for a while to us they were indistinguishable. We just knew they were part of the faculty. And then gradually, as time went on, of course, we did get to know them. However, I do remember one particular thing about him, and that was that one day I was hand computing one of these trajectories. Now, this may have been any time during the first year I worked there. He said to me, "How would you like to have a machine that would do this computation automatically?" And I said, "Well, what do you mean automatically?" And he said, "Well, when you do a multiplication right now, you write down the results, and then when you do the square root, you write down the result of that, and so on." There were quite a series of of computation that went into just computing one line of the ballistics equation. So he said this machine would, instead of you're having to write down each number, the result of each multiplication, it would keep it in the machine and then go on and perform the next operation. And as I envisioned it, and I don't remember his exact words, as I envisioned it, it was something like a very large desk calculator that would put out for you, read out for you at the end of each line a number which you could write down, and you hand computed this trajectory in one sense that it would do a whole line of computations, which was about 20 operations, which included looking up a table and doing a square root and doing a couple multiplications. This would all be done automatically inside the machine. I thought that was just great. I thought that was wonderful. Well, a couple years later, in 1944, one day Mauchly and Eckert came down to the analyzer room one evening, and they said, "Would you girls like to come up and see what we've just done?" I think this was the week that they had finally gotten 2 accumulators to work. We went upstairs, and there they had these 2 accumulators, the first, you might say, building blocks of the ENIAC, were now completed and ready for operation, and this was about April of '44. And they said, "Watch this," and they pressed, or John, I don't remember which one, put the number 5 in, and they said, they pushed this little button. They had a little handheld, a wire coming from the machine with a little button on the end of it, and flip the 5 seemed to go over to the other accumulator but moved over 3 places, so you got 5,000. And they said, "There, you've multiplied by 5 by 1,000." And we said, "What?" The other girl with me was a girl by the name of Alice Snyder, and we were both amazed because it required all this equipment to multiply 5 by 1,000. Of course, we were pretty stupid and naive and really didn't understand the implications of the machine at all. That was, by then, we had sorted out who the different professors were, and we realized that at that time, Eckert and Mauchly and a number of the other engineers, Kite Sharpless and Bob Shaw, and I've forgotten just who they all were, but they were working on what we regard as a secret project. And we had never been permitted into that room before the night that we saw those 2 accumulators working.
Were you part of all those girls that then were working on the trajectories at one time when I've heard the stories of about 100 or so? Were you?
Well, the way of the project started out in Aberdeen, for the Aberdeen Proving Grounds. The Aberdeen Proving Grounds Ballistics Laboratory sent a nucleus of about 10 people to Philadelphia, and they thought that Philadelphia was a fertile area and they'd be able to pick up a lot of girls who were math majors. Well, as it finally worked out, Fran and I were the only 2 math majors they were able to pick up in the area. A lot of girls who might have majored in math in college went into teaching or something of that sort, I don't know. But they began to bring in girls from other cities. Now, I understand Arthur Burke's wife, Alice Rowe Burks, who lived in Ohio, was one of the first people to come there that summer, and she had been a math major. So they gradually began to bring people in who were math majors from other cities. Well, that fall, I think they had pretty much exhausted what they thought was the available supply of math majors, because they were in competition with the Navy, who were trying to pick up girls to do the same type of ballistics calculations up at MIT or somewhere in the Boston Navy Yard. So then I think shortly after Dr. Goldstein came there, he had his wife set up a course in which they would try to teach the girls something about, girls who were interested in math at all, something about calculus, and teach them how to do the ballistics equations. So that was the beginning of a great, you might say, enterprise that went on there at the Moore School for the next couple years. Mrs. Goldstein, I think, went around the country recruiting girls who had at least 2 years of experience of college math. And they managed to find about 30 girls, and Mrs. Goldstein, along with